All right, let's take one more minute on this problem. All right, so you've had a fair few minutes to stare at this weird looking circuit here. What does this do? Raise your hand if you think it's a latch. Raise your hand if you think it's a flip-flop. Raise your hand if you're not really sure what the heck this does. All right, let's find out. Um, when you see a weird looking circuit like this, often the easiest way to approach it is as with any other circuit where we just draw our truth table and analyze it. And this isn't too bad here. This circuit happens to only have two inputs, right? Clock and D, which happen to be the same inputs that a flop or a latch would have. So let's look at the four cases in our truth table. First, let's take the case where clock is 1, actually, because that's a little more straightforward to see what's going on. So what happens when clock is 1? Well, that's being fed into this NOR gate. So if clock is 1, that's always going to force S and R both to be 0, exactly. So if R and S are 0, now what's happening here in this weird circuit here? This is a cross-coupled circuit, right? Where the outputs are being fed back into the inputs. So if R and S are 0, then they're not really doing anything into these NOR gates, right? The value of the NOR gate just depends on the other input. So if the other input here is 1, then the output's going to be 1. Then the output's going to be 0, rather, because it's inverting. Same here. If this is 1, then this is 0, and vice versa. If this is 0, then this is 1, and vice versa. So what is this cross-coupled circuit doing when R and S are 0 like this? Let's look at an example. If Q is 0, then this is 0, then Q bar is 1, right? It inverts through the NOR gate. Then this input is 1, and so Q stays as 0, right? So what is this doing? It's not really doing anything, right? It's holding its previous value. And this is very similar to the cross-coupled inverter that we saw in the previous lecture when we were discussing latches, where the output is fed back into the input in order to hold the previous value. Okay, so that's a little weird, but that's what's going on. That's half of our truth table. Let me erase the markings here. Okay, so what about these other cases? If clock is 0, then we have to look at what's going on with D, right? So in this first line, if clock is 0 and D is 0, then R is, what is R? Say it a little louder so everyone can hear you. Yes, yes, yes. R is 1. Okay, but here we have D bar going into the NOR gate, so S is going to be 0. So if R is 1, then that necessarily forces Q to be 0 through the NOR gate, right? The NOR gate inverts and forces it to 0. Okay, let's look at the other case. If D is 1, now R has to be 0, but S is going to be 1. So you can see this is going to be the inverse case of the other. And so if S is 1, then that forces Q bar to be 0. And so Q ends up being 1. So this is our truth table. It can be a little challenging to reason through it, I think. Mainly if you don't have intuition around these inverting gates, like what happens through a NOR gate. It might be helpful to draw out a little truth table of the NOR gate to remind yourself of the behavior there. But we looked at each case. This is what's going on. So now we just need to think about what the behavior is, right? So when the clock and D inputs are like so, this is the behavior of the output Q. And so in particular, when clock is high, it stores the value of Q previous. When clock is low, it passes through the value of D to Q. So what kind of circuit is this? I think most of you had it right. That's right, it's a latch. And is this an active high or an active low latch? This is a transparent low latch, right? Because when clock is low, it's transparent. So this is the opposite flavor of what we mostly looked at last week. But nonetheless, it's a latch. For those of you current on the discussion, you'll recognize this part of the circuit as something called an SR latch. S for set, because it forces the value to 1. R for reset, because it forces the value to 0. And then if R and S are both low, then it just stores the previous value. And so all this circuit is doing is converting that sort of SR latch specific behavior into a generic latch that we're used to looking at from last week. So any questions about this one? Yes. Oh, good question. So let's see, when the clock rises, or rather when the clock falls in this case to make the latch transparent. And let's assume D is already switched to the previous value, right? So then the path would be through one NOR gate and then a second NOR gate. So it'd be two NOR delays. The details depend on how they're sized, of course, but you could analyze that to figure out the delay. And it's pretty short. It's just two combinational gate stages. Uh, so Right. So I guess it depends whether you're switching Q from 0 to 1 or 1 to 0. Right. One of the paths is through these two gates, and then another path, and then Q bar will switch after a delay. So there's a mismatch between the delay to D and the delay to D bar. Right. The other path would be through here and then through the feedback to switch Q. And so that would be three gates. So I guess in the worst case, you're correct. You would want to time it for the three gate delay. Yeah. All right. The diagram has become very messy and full of dots. I hope that's okay. Other questions on the warm-up? Yeah, it can be a bit uh, uh, challenging to wrap our heads around these sequential circuits, especially if you feel like you've mastered combinational logic and understanding its functionality from the first half of the course. This kind of throws a curveball, right? We have all this weird stuff going on. We have feedback. We have nodes that depend on the current state rather than just the inputs like combinational logic. We even saw the case last week where we had a fight between two different drivers, and one had to be stronger than the other in order to win the contest. So there does tend to be a little bit of stepping outside the box in order to design these combinational circuits. But keep your wits about you. Just draw the truth table, think about all the cases, and then try to reason about what the behavior is and which kind of circuit it matches. Okay, so let's summarize from last week. Or I guess this would be 2 weeks ago now, of course, because last Tuesday we had our special guest lecturer from NVIDIA on formal verification. I encourage you to watch the recording if you missed it. But 2 weeks ago, when we last spoke, we talked about these two critical sequential circuits, latches and flip-flops, where latches, as we just saw retain their state when they're not transparent. And you can build them using these cross-coupled inverters or other cross-coupled circuits. Also commonly these transmission gates, which again were kind of weird compared to previous CMOS logic we looked at. And then we talked about how to build flip-flops, which is very easy once you can build a latch, because a flip-flop is just two latches. But the behavior changes. And so a flip-flop toggles only on the rising edge of the clock, unlike the latch, which passes data as long as the clock is high. So let's move on to SRAMs. Recall that at the very end of the last lecture, we started talking about how flip-flops are nice for storing one bit or a handful of bits here or there. But if you want to store a lot of bits, thousands or millions of bits, like in a cache or a register file or some other large memory structure that are very common in almost any kind of digital circuit you might want to build. Well, flip-flops ain't going to cut it, right? It's not going to be efficient to lay down millions and millions of these cells, each of which is 12 or more transistors inside a flip-flop. And so instead, engineers came up with this structure called an SRAM. And today we're going to talk about what it is, the basics of how it works, and how you might think about building and constructing and using them. We're going to start this today. We're going to finish it up on Thursday. So let's get into it. SRAM, static random access memory. Some of you may be familiar with that acronym already, but let's be clear about what it means. So random access memory, or RAM, just means we can read and write to arbitrary parts of the memory each cycle. We don't have to read in order or write in order. With an SRAM, we're going to be reading one whole word at a time. So a word might be 32 bits or 64 bits or 128 bits. We're not reading and writing individual bits in an SRAM. We're reading and writing whole words at a time. We're going to see why, based on how the SRAM is designed to maximize the area efficiency. So that's random access. Static just means that the memory holds its state indefinitely as long as you power it. So it has internal positive feedback. That means that each bit, if it's a one, it keeps being a one. If it's a zero, it keeps being a zero. This might seem obvious, but there are types of memory, such as DRAM, dynamic random access memory, for which this is not the case. So in a DRAM, even if it's powered, the charge on a bit cell will eventually leak away. And so DRAM has to refresh its contents every so often, every 20 milliseconds or 50 milliseconds in order to maintain its state. We're not going to talk about DRAM in this class. And SRAM, you don't need to do refresh or anything like that. It remembers as long as it has power. So in an SRAM, each cycle, we're going to either read or write a single row, and a row in the diagram, this is an example of a row. And these are the columns. A row is also called a word in the SRAM. We use those terms synonymously here. And each column stores a bit. And so every cycle, if we want to read or write, we're going to activate exactly one row and then read the bits out of that row or write the bits into that row, 1 bit per column. The SRAM basically has two parts. We're going to talk about them in turn. So this array of many, many similar looking things, this is called the bit cell array. It is what it looks like. It's just this two-dimensional grid of lots and lots of cells, each of which stores 1 bit. These cells are super highly optimized for area. And so each of these individual cells winds up being way, way smaller than a flip-flop. This is the main reason to use SRAM, is to take advantage of these very, very highly optimized, very squeezed in bit cells in this regular structure. Okay, and then the other parts of the SRAM are the periphery. So that's everything that's not the array. So you'll see denoted here, column circuitry, the row decoder, this bit line conditioning up top. This is all periphery. And we're going to talk about the periphery circuits second, so don't worry too much about those for now. Just keep in mind that they exist. We're going to focus on how to build the array first, and in particular, how to design a single bit cell inside of that array. Because once you've designed 1 bit cell, you're done, right? You just build however many of them you want in a grid. So if we can design a good bit cell, then we understand how to build the array. Okay, any questions about the basics of SRAM? Very, very high level stuff before we get into the details. All right, let's build a bit cell. This is a very basic static memory element. It has 2 inverters. Recall from last time we spoke that in this cross-coupled inverter pair, if D is 1, then it gets inverted. And so, D bar is 0. And then that gets inverted. And so D is 1. And so D bar is 0. And D is 1. And D, right? It's in feedback. It's in positive feedback. It keeps its value indefinitely as long as you're supplying power to the inverters. This is the exact same cross-coupled inverter circuit that we used to build our latches last time. So far, so good. This is going to be the core elements of our bit cell. Now, the trick is, how do we actually make use of this thing, right? Because we need to do 2 things. We need to read from it the value, and we need to write to it. And we can't do either of those things right now. So let's modify this. In particular, let's add an NMOS enable circuit, or an NMOS enable transistor on the left-hand side here. So let's think about how this works. Now, if this storage node is 1 and 0, right, we're in positive feedback. If the enable is low, then that positive feedback continues uninterrupted, right? No problem. The NMOS is off. Now, let's say we want to write a 0 into this cell. So we'll set D to 0. We'll pull the enable high to 1, which turns on the NMOS. What's going to happen? Well, we see something very interesting, which is that this transistor, the enable transistor, is trying to pull down the value from 1 to 0, but it's fighting against this feedback inverter, which has an input value of 0, and so it's trying to output a 1 still. So this is another case where we have contention, we have a fight between two different parts of our bit cell. And so we need to make sure that this NMOS enable transistor is sized large enough and has a low enough resistance that it's going to win the fight. It's going to overpower the feedback in the loop, and eventually it's going to flip this node to a 0, which then will be fed back and flip the other node, the inverted node, to a 1. So this is sort of the core concept about SRAM bit cells, is that in order to squeeze things and use as few transistors as possible, we're not relying on kind of contention-free CMOS like we did in our combinational circuits. Instead, there's always going to be contention anytime we want to do something. There's always going to be a fight between two different transistors. And rather than just relying on the topology, we need to rely on the sizing in order to make sure that the behavior is correct. Yes. We'll talk about that in a couple slides. Yeah. Good question, but hold on to it for now. So let's finish thinking about this. Now, let's say we have a 0 now in this left node and a 1 in the right node. Now we want to write a 1 into this cell. Recall that NMOS are really good at pulling down, right? That's why we use them in the pull down network. But NMOS are really crummy at pulling up. You wind up with a threshold voltage gap between the value you want and the value you get. So this 5T, 5 transistor SRAM cell, you can sort of only write it in one direction. You can only pull it down into this 0 on the left, 1 on the right state. But you'd have a really hard time actually pulling it back up because NMOS are no good at that. So one option, I guess, would be you could add a PMOS to do the pulling up. But a more common option to design the classic 6T bit cell in our SRAMs is that we're just going to add another NMOS on the other side. This makes the sizing easier. This makes the layout easier because it's symmetric. It's easy to reason about. And so now we have this nice case where you're always pulling down with an NMOS if you want to write. If you want to write D to be 0, right, then this left-hand node is going to be pulling down, and the right-hand node is not going to be doing much. If you want to write D to be 1, well, then D bar is going to be 0. And this NMOS is going to be doing the hard work on the right, and the left-hand NMOS is not going to be doing much. So this is our classic SRAM bit cell. It's symmetric, it's differential, which means that everything has its complements in the cell. And we access it through these access transistors that are getting the enable signal in order to either pull down one side or pull down the other side in order to take advantage of the strength of the NMOS. This is the exact same thing. It looks a lot more intimidating because it's all transistors, but all we've done is write the inverters with their as NMOS and PMOS transistors, which if you think about it is not too scary, right? So here's an inverter. Here's an inverter. And the output of this inverter is being passed into the input of the other and vice versa. So this is the exact same cross-coupled inverter that we saw in the previous slide. It's just translated into transistors. We've numbered the transistors M1 through M6 in order to keep track of which one is what. We'll use that in our analysis shortly. And then you'll notice that we've wired up all of the inputs of the cell. In particular, those enable pins on M5 and M6, which are sometimes called the access transistors for reasons that will shortly become very clear. Those are wired to the word line, or WL, which goes across the array to activate a whole word of bit cells at a time. So yeah, to be clear, M5 and M6 are the access transistors. And then the inverter consists of the pull up transistors, which ones are the pull up network here? Which ones are pull up? Yeah. That's right. Yeah, the PMOS in the inverters, M2 and M4. And then we have the remaining ones are the pull down, M1 and M3. Okay, so that's our terminology. And then you'll notice that the values that we want to read or write into the transistor have been wired to the bit lines, or BL. And we have bit line on the left and bit line bar on the right, its complement. So the word line says, are we accessing the cell or not? Right? If the word line is off, it's just those cross-coupled inverters and feedback. If the word line is on, then we're accessing the cell in some way. We're either reading or writing. And then the bit lines are sending in or reading out the actual data into or out of the cell. Okay, we're gonna go in much more detail into exactly how the write and read operations work in a second. But first of all, are there any questions about the bit cell so far or how it's wired up? Yes. Baseline bar reaching and read from the same time or like one of the. Yeah, so it would always be at the same time. So as we'll see in a moment, but you're always going to be making use of bitline and bitline bar sort of simultaneously in order to do a read or a write. In general, it's only one side or the other that's sort of doing the work. This will become a little more apparent when we go through the examples. but each bit cell, each column has its own bit line and bit line bar, right, in the array. Okay, so let's think about how to read and write this thing. We've returned to the much less scary looking diagram with the cross-coupled inverters for this analysis. Hopefully, in your mind, you will start to feel fluent at kind of moving back and forth between the diagram with 6 transistors and this diagram here, because they're exactly the same. So let's talk about the sequence to write a bit cell. Okay, you notice that this bit cell is storing a 1. By convention, we call the node on the left to be Q, which is the actual quote unquote value in the cell, although everything's differential, so it doesn't really matter. And then on the right is Q bar. So we're storing a 1, and we want to write a 0. So what we're going to do first is we're going to set our bit line to 0. We're also going to set bit line bar to 1, although that won't do as much, because as we discussed, NMOS are really bad at pulling up. So the right-hand side is not really going to contribute much here. It's mainly the left-hand side that's going to perform this write. Oops. Okay, and then our word line starts low, and to initiate the write, we're going to set the word line high. Okay, you can see in this timing diagram a little more detail about what's going on. This timing diagram on the right of the slide. So word line goes high. In this example, they're putting bit line low at the same time as word line going high, but that's fine. You can do it either way. So bit line goes low. And well, what does that mean? This is that same fight that we looked at a couple of slides ago, right? Where this inverter, the feedback inverter, or particularly the PMOS, the pull up transistor in that inverter, is trying to pull up the node Q to 1, but the access transistor is trying to pull down Q to 0. So they have this fight. Q doesn't transition right away, right? It's in contention. But eventually, the stronger NMOS wins the fight. And so Q pulls down. So this node goes to 0. And then once this node is going to 0, then the top inverter is going to quickly push this node to 1. And so you can see Q bar going high here in the timing diagram. And that completes our write operation. So key things to keep in mind here, this circuit is, again, it's differential. So it means both halves eventually wind up in complementary state. But when you're performing a write or a read, as we'll see, it's really only one side that's actually doing the work. That's actually forcing the transition to happen or forcing the value to change. And then the other side kind of follows along later. Right? Once the word line is activated here, when bit line bar is a 1 and Q bar is a 0, yeah, this NMOS is going to try to pull up that node, but NMOS is does such a bad job at pulling up the node. Right? You can see that here in the timing diagram. It's pulling up a little bit, but not enough to win the fight. So the work is really being done on the left side in this example when we're writing a 0 into the cell. The other case shown on this slide is much simpler to analyze. There's no transitions. When we want the cell to hold its value, we just leave word line low. And that means the access transistors never turn on. And that means the cross-coupled inverters maintain their feedback for as long as they like. Right? Q is 1, so Q bar is 0, so Q is 1, so Q bar is 0. Okay, so that's right. That's one of the things we need to do with this bit cell. The other one is a read. We haven't talked about that one yet. Let's look at that now. So a read, we need to be careful about a different thing, right? The write, we wanted to make sure that the value flips eventually. The read, we need to make sure that the value doesn't flip accidentally. So let's think about how to read this cell. What we're going to do for a read is we're going to pre-charge both bit lines to 1. So bitline and bitline bar are both being set to 1. It's kind of weird. Usually if something is the complement of something else, it has the opposite value. But again, in order to pack all these cells into these tiny SRAMs, only 6 transistors each, we need to cut some corners. Okay, so we're gonna do the read operation by setting both bit lines high. And then we're going to turn on the word line. So now let's think about what's happening as we turn on the word line. Well, on the left-hand side, both sides of that access transistor are 1, right? So nothing's happening. So bit line is keeping its value. On the right-hand side, the bit line, right bit line or bit line bar is 1, but the Q bar node here is 0. Right? This is Q bar. This is Q. So once again, we have a fight where the bit line is being driven now by, it's being pulled down by the NMOS in this lower inverter. And so what's going to happen, these bit lines are very long, right? There's a huge capacitance of these many, many hundreds of transistors sitting on this bit line, as well as this very long wire. And so this bit line is going to start to decrease, but very slowly. You can see that in the timing diagram here. Word line goes high, and the bit line starts to decrease very slowly. So that's pulling down the bit line, right, based on the NMOS in this inverter. But what we need to make sure is that we don't flip any of the nodes, of the storage nodes in the cell, right? So you can see once again that there's a fight where Q, well, I guess this diagram is opposite of what I've labeled it here. So in this example, we'll treat, or for the purposes of this drawing, we'll treat the right side as Q and the left side as Q bar, which is a little confusing. Sorry for that. Right, you see there's contention where Q rises a little bit. It's trying to be pulled up by the feedback. And so we need to make sure that the cells are sized in order to win the fight and keep the cell with its current value. So let me talk now exactly about the sizing challenges that we need to solve, and then we'll take any questions about the write operation and the read operation. So there's 2 constraints that we need to be careful about. One is read stability. This is what we just talked about. The cell should not change the value during read. Okay, so let's consider this example. If Q is 0, then, and the word line is 1, because we're reading, then M5 and M1 are both on. Right? So M1 is trying to pull Q down to keep it at 0, but M5 is trying to pull Q up to match the bit line. This is contention. And the problem is that if Q gets too high, then it's going to flip the bit, which is not what we want in a read. So you can think of this as a voltage divider between M5 and M1. When these transistors are both on, right, we can just model them as resistors with an on resistance. And this is our node Q. And we need to make sure that Q stays 0 or close to 0 so that it doesn't trip the feedback and flip the value of the cell. So if we want Q to stay close to 0, which resistance do we need to be smaller? Careful, we want the size of the transistor to be larger, so the resistance is smaller, right? So let me try to phrase the question as clearly as possible. Which transistor do we want to be larger in order to make sure that Q stays close to 0? Yeah. Right. We want the pull down transistor to be large so that the resistance is small. So we want R1 to be less than R5. So that means we want the size written here as width over length of the transistor, right? Because recall that sizing transistor widths wider makes them stronger, makes the resistance lower. So we want the size of transistor 1 to be larger than the size of transistor 5 in order to ensure the read stability of the cell, in order to ensure that node Q does not flip while we're reading it. Right? If M5 and M1 were equal size, then Q, the value of Q, the voltage at Q, would go to VDD over 2 during the read, which is undesirable, right? That might be enough to flip the value being output by the other inverter, and then that would flip the cell. So we want to have lots of margin to make sure that Q stays low. So the typical way to size this is that you would set the size of M1 to be 50% larger than the size of M5. Unfortunately, with FinFET nodes, sizing in SRAMs became a lot more challenging because in FinFETs, you don't get to size an arbitrary width. You only get to count fins, right? So in FinFETs, typically you would just size you would size M1 to be double the size of M5. In the very latest processes that are just being released now, which are gate-all-around, you once again can have continuous sizing, at least in theory. So I don't actually know if SRAMs are going to go back to these more carefully ratioed designs. That'll be interesting to see. In case any of you get your hands on a Intel or on a Intel 18A PDK sometime. But the key takeaway is that M1 needs to be larger than M5. M1 needs to be stronger than M5 to ensure that the node stays pulled down during the read operation and wins the fight. Okay, yes, question.
So, in order to write M5 had to be stronger than M2, correct?
Yes.
So does that so that means the inverter M2, M1 is going to be like really asymmetric?
Yes. Yes. So,
Worry about that?
well, let's take a look. Okay, let's talk about writability next. And then we'll think about all of the ratios together. So recall that for writability, now M5 is trying to pull down, but M2 is trying to pull up. And so we once again have a fight. We have this voltage divider. But this time we want Q to flip. We want Q to go from 0 to 1. Right? So we want the voltage of Q to be as close to VDD as possible. So that means that now we have the opposite case where the access transistor needs to be stronger, larger than the pull up transistor. So for writability, we need to make sure that we can successfully write the bit line voltage into Q. We can overpower the PMOS transistor in the feedback. And so again, we have this ratio constraint. In old planar processes, right, PMOS used to be weaker than NMOS. So you would kind of get this for free just by setting them to equal size. But as we've discussed in FinFET, that's no longer true. And so we once again would double up. We would say the access transistor M5 has to be twice the size of the pull-up transistor M2. And so you're absolutely right. You end up with this sort of three-way constraint, right? M1 has to be stronger than M5. M5 has to be stronger than M2. And so one option is just to size them as one fin and then two fins and then three fins. So this is the sizing of M2 to M5 to M3. You will also see SRAM bit cell designs where the sizing is 1 to 2 to 2, where the two NMOSs are actually sized the same way, are set to the same size, and then you have to use other tricks to make sure that M1 is actually stronger than M5. Because there's other ways to modify the resistance equivalent of a transistor besides just sizing. So you can make a 1 to 2 to 2 ratio cell work with some care. All right. Any questions about the SRAM bit cell and how to size and ratio the transistors inside it for writability and read stability? Okay. Let's give this problem a try. The pull everywhere is not really working too well today. So just go ahead and work it out on your own notes, and then we'll discuss it.
It's just the style of the right. Like for BT, the size should bend this goes like this. Like this is it's more than 5 cents. Like sort of. Yeah, I do go up to the so I think it's on the
Okay, so hopefully you've found a few transistors that are on in this scenario. Please go ahead and actually let's just call in a few folks for this one. So who can name one of the transistors that's on? Yes. Sure. M5 is on because the word line is high. So far, so good. Who else has one? Yes. Yeah, M6 is also on. Also connected to the word line, which is high. Any others? Yes. Okay, so M3 is on because, well, what is Q set to? Q is set to 0, right? So does a 0 turn on an NMOS? Yeah, okay, that's better. And M4 is going to be on, right? Because Q is 0, which is tied to the input there. 0 turns on the PMOS. We haven't done the right yet. Yeah. Right, and then Q bar is set to 1, and so that's also going to turn on M1. Yeah. That's right. So there are 4 transistors on in this scenario before we perform the write. And then, of course, after the write goes through, Q and Q bar will flip. And so then M2 and M3 will turn on after the write. And then we'll turn off M5 and M6 to complete the transaction. Questions about this? Yeah, SRAMs and SRAM bit cells in particular, this is tricky stuff. This is probably the most non-intuitive circuit that we will look at all semester. So don't feel too overwhelmed or frustrated if it's not clicking right away. You'll get some more practice on your homework. We'll talk about it in discussion this week as well. But these SRAMs, and in particular the SRAM bit cell, are super important, and they show up all the time in your digital logic. And so it's really good to understand them. Okay, time for a break. Talk to your neighbor for 2 minutes. I'm very sure everyone can think of one thing. I haven't been able to program that.
It's just the fact that it was the voter actually. Yeah, he is like.
All right. Let's come back together. Give me a thumbs up if you thought of one joyful thing in your life. Everyone thought of one joyful thing in your life? All right. Yeah. See, things are not so bad, even though it's crunch time. You'll get through it. We'll all be standing at the end. Let's talk about where we are in the course, which I think should not have many surprises at this point. Welcome back from Thanksgiving. Our final homework is going to be due this Friday. It's talking about latches and flip-flops and SRAM. There will be a small portion of the homework that is based on content from Thursday's lecture. So apologies for that, but because of everything coming to the end at the same time, there's sort of no way around it. So if you do want to start early, you can do about 90% of the homework without what you need from Thursday's lecture. Of course, the elephant in the room is the project. It's ongoing. I hope people took a little bit of time off from late night debugging sessions during the break. Please do keep pushing on checkpoints 2 and 3. Even if you haven't submitted them yet, you will still get late credit. Ultimately, our goal is to have everyone have a finished working processor by the final checkoff, right? So that's sort of the baseline for success here. Checkpoint 4 and the design contest for optimization are in progress. If you have finished all of the sort of functionality and you're ready to make it go real fast. So that's ongoing. And then we're going to announce soon the logistics for the final project checkoffs, which will be taking place next week. So during RRR week, you and your partner are going to need to come to the lab and talk about your processor design and how it works and go over the final materials. Okay. Again, we're going to put out more details of that very soon, but that's at a high level what's going to happen. And then lastly, of course, I assume folks know this, but just a reminder that our final exam is scheduled for December 16th. That's 2 weeks from today, from 3 to 6 p.m. It's a cumulative exam, so it will include everything from the whole semester of the class. And there's some details about that on Ed already. And again, we'll be posting much more details as we get closer to the exam. Okay, any logistical questions? Yes.
Or is purely an optional competition? There's no minimum performance level we have to hit?
Correct. Yes. This semester, there's not a minimum figure of merit. Okay. Just pass all the tests. Okay. So we're going to spend the last 15 minutes. We're going to start talking about the second half of the SRAM, which is the periphery. I think we'll probably talk about row circuitry today and then column circuitry on Thursday. Okay. As a reminder, the periphery is everything that's not the array of bit cells, right? So the bit cells are often a majority of the area in these SRAMs, but the periphery is a pretty sizable area as well. And it's sort of you can think of it as a tax or an overhead, right? We have this really, really compact, efficient storage in the bit cell array, but then we need all this extra stuff on the outside in order to read and write it because this individual cells themselves are so simplified. Compare this with a flip-flop, which is standalone, right? You don't need any special circuitry to read or write a flip-flop. It's all kind of baked into the flip-flop itself. An SRAM, you would never see an SRAM bit cell by itself in a design. It's useless. You need this periphery in order to use it. And so today we're going to talk about the row decoder, the row circuitry, which is arrayed kind of along the vertical axis, the left-hand side of the array. The sort of schematic-ish cartoon that you see here is actually very similar to what a real SRAM layout looks like. An array of bit cells in the middle, and then periphery circuitry around the edges in a rectangular pattern. All right, let's talk about the row decoder. The row decoder's job is, given an address, figure out which row to activate. Not too scary. Let's see how it works. So once again, we need to activate exactly one row of the SRAM at a time, right? Because we want to read one bit out of each column. So we can never have more than one row active. So how do we do that? Well, one option for an n bit or an n entry SRAM would just be to have n address bits, right? So you would have, in your Verilog, you might write input right. So for a 256 entry SRAM, you just have 256 bits of address. And then you turn on whichever bit you want. So that's one way to do it. That's what's shown on the left here. It's a lot of bits. Right? Adding a new bit for each row, a new address bit for each row is very inefficient. There's too many select signals, too many wires to route everywhere. So instead, what we'd like to do is for, say, n equals 256 as the example I'm showing here. Let's instead, use binary, not a one-hot encoding for our address. Don't forget the semicolons, of course. And so now we can just have an 8-bit address to select between these 256 different words. Right? So this is very nice. We've reduced the number of select signals from n to log base 2 of n. And it means we can have very deep SRAMs with many entries. You'll typically find SRAMs up to 1,024 entries deep. That's pretty common. Occasionally, you might find even deeper ones of 2 to the 11th or 2 to the 12th. So that's 2,048 or 4,096 entries. But in any case, you're never going to have more than, 15 bits of address or usually even less. Okay, so that's nice. But now we need to decode that log 2 of n bits of address into the actual one-hot word select encoding that we want. So here's a very naive way to do that. Here we have n equals 512. So we have 512 rows in our SRAM now. That means we're going to have log base 2 of 512, which is 9 bits of address. And we can just write down the Boolean equations that say, for any set of bits, if those bits are all 0, well, we'll take A0 bar, A1 bar, A2 bar, A8 bar, A9 bar. That selects our word line 0, right? And then continue this pattern. Anytime the address is a 0, you take the complemented input and AND it. Anytime the address is a 1, you take the input itself and AND it. So selecting the last row, the 511th row, would be if all the bits are 1, ANDed together. So you would build this thing just out of 512 big old 9 input AND gates. Right, you can see a much simpler, the schematic for a much simpler example, which is just a 3-bit or 8 entry SRAM with a 3-bit address on the right. And it's just this whole sea of AND gates with different patterns of inversion on the inputs. And hopefully you can convince yourself that only exactly one of these outputs is going to go high at a time, which is what we want, right? So that's our row decoder. If we wanted, we could stop there, but it turns out we can do a little better than that. Okay, first, just as a reminder, And we're gonna look at this 256 by 256 block for the remainder of the examples. This is where the decoder is sitting on the left here, and its job is to assert exactly one of the word lines each cycle. Right, so that means all of the bit cells are not doing anything except for the bit cells in the row where the word line is activated. Because we saw that when we activate the word line, that's going to turn on the access transistors, and that's going to perform our read or our write, depending on how the bit lines are configured. So that's the job of the decoder. Let's try to do a little bit more cleverness on the design for this 256 entry SRAM. So as we said, we could build it out of AND gates, 256 8-input AND gates. And with 16 address lines where we take our original 8 bits of address and then invert them. So we have A0, A0 bar, A1, A1 bar, A2, A2 bar, right? We have each address bit in its complement makes 16 address lines for a 256 entry SRAM. One problem with this design is that each of these address lines is needing to feed exactly half of those big AND gates, right? So think back to your logical effort. What's the ideal number of kind of gates of fan out that we like to drive for optimal delay? We like to have fan out of 4, right? Well, in this example, each address line has fan out of 128. So it's too much. You end up needing to add a whole lot of buffering in the front. Not very efficient in an area or energy. It makes the layout more complicated. So let's try to do a little better. Here are the last 2 combinational logic blocks for the last 2 lines in the rodecoder, right? Calculating word line 254 and word line 255. Right, so word line 255 takes all of the high inputs, all of the true inputs of the address. 254 is the same, except for it complements the LSB. Okay, and here's the logic. Right, this is a big AND gate kind of decoded into many different AND gates and then complemented. What do we notice? There's a lot of similarities, right? In particular, this structure shows up in both of those trees. This structure shows up in both of those trees. This structure shows up in both of those trees, right? The only difference is that LSB, that A0 bar versus A0. But do you see that these circled sets of computation are totally redundant? It's just taking the same inputs as for that part of the tree and doing the same computation in each case. So let's factor out the redundant gates. This is the concept of a predecoder. So we're going to use a single gate for each of the shared terms in that first stage. Right? In particular, we'll take, for example, the first 2 bits. We have A0, A0 bar, A1, A1 bar. And we're going to AND those together in all 4 possible combinations first. And then we're going to use the output of that in the subsequent stages of the decoder. Right? We're factoring out that common logic that's redundant across many, many different rows of the decoder and moving it into this predecoder stage. So this is an example of what that looks like, right? So for A0, A1, we take all 4 possible inputs, right? We can label this A0, A0 bar, A1, A1 bar. We take all four possible combinations and AND them together. And then we do the same for A2 and A3. We do the same for A4 and A5. And we get this whole mess of pre-decoded signals where we've kind of pre-calculated in the first stage the different combinations of those ANDs. And then we start pulling off of those pre-decoded signals for the next stage. This is way more area efficient. It saves a whole bunch of redundant logic by grabbing all those redundant parts and moving them in a single copy into the predecoder. And you'll notice that this has a couple more nice properties, right? One is that it's still a very regular logic pattern, which is very important for SRAMs because you need to do what's called pitch matching. So every row of the array, you need to fit the decoder logic in the same pitch as that row of the bit cells. Regular logic makes it much easier to do that layout. The second nice thing about this is that our problem of big buffers has gone away, right, at the front, because each input is no longer driving 128 things. It's only driving 4 things. So we've eliminated the pain of those massive buffers as well. So that's the basic concept of pre-decoding. We're not going to go into more details than this. You can imagine that you could even do multiple stages of pre-decoding if you wanted to, in order to further optimize this. There are trade-offs in terms of wire length versus gate cell count and so forth, which are interesting to think about and analyze in SRAM design. But that's the basic idea of a pre-decoder. Okay, we're just about out of time. So let me summarize, and then I'll stick around for a few minutes if folks do have questions on that last bit. Today we talked about SRAMs. The whole point of SRAMs is to cram a lot of storage into a small area. We do that by specializing these very special bit cells into an array, a massive array. Each bit cell stores 1 bit. We have to design the bit cells very carefully because we're doing some pretty unusual things to read and write them compared to normal CMOS logic. In particular, every time you read or write, there is a fight, there's a contest, there's a resistive divider. And so we need to carefully size those transistors to make sure that the cell is writable, so the write wins the fight, but it's also read stable so that the read doesn't flip the cell. And then we just talked about row decoders that use the address bits to activate exactly 1 word line and how we can optimize those with pre-decoder logic. All right, let's call it there for today. We'll pick up with the last little bit of column circuitry on Thursday. Thanks, everyone.